So the seventh question of CodeChef starter 119 division 4 is Xorred. In this question, we are given an array of length m, and an array of length m is called magical if the bitwise AND of that array equals to the bitwise OR. So basically, all the elements, if ANDed, should be equals to all the elements OR, right?
Yeah.
And like for example, they have mentioned 111 is a magical array because the bitwise OR and AND are both equal, but 11 is not. Okay. And we are also given now in the question we are given an array A of length n, and we need to find the number of subarrays that are magical. Okay.
Yeah.
So a subarray is basically a contiguous segment in the array, and we need to find the number of subarrays that are magical. Okay.
Yeah.
Now in the first test case, we have, or let's go to the second test case. Okay. In this test case, we are given an array of size 3. We have 111. So the number of subarrays will basically be either the first element, second element, or third, or the all three elements, right? Those are the four possible subarrays that will give the AND and XOR value as the same.
Yeah.
And the constraints in this question are test cases are up to 10 power 5, n value is up to 10 power 5, and A of 5 value is up to 2 power 15. And they've also mentioned that the sum of n over all test cases does not exceed 10 power 5. So this is also one important constraint.
Yeah.
So since the n value is up to 10 power 5, we cannot use the approach that takes O of n square. We will have to use the approach that takes O of n or O of log n. Okay. So yeah, anyways, let's see how we can solve this question.
So basically here, let's consider an array. Let's say it's 0 based. A0, A1, A2, so on till AN minus 1.
Right.
This is the array that we have.
Yeah.
Now, firstly, let us fix a point and then make one observation related to AND. So basically, we are fixing the rightmost point of a subarray.
Right.
Is what we are assuming. So let's say this is the leftmost point of the subarray. Let's say this is the leftmost point L. So now the claim here is from this point we keep on taking AND, right?
Yeah.
So let's say initially what can our AND value be? So initially AND value can be A0 itself, right?
Yeah.
Now after ANDing these two things, let's say still AND value is A0.
Okay.
Right? Then let's extend it and find out a point where AND value changes, right?
Okay.
So for that, let's say for now, we have A3, A4, A5, AN minus. And let's say this is the point where AND value changes. That is, if we consider A0 till A4, then AND value is different. It's not equal to A0. That means, can we say that in this the AND value is X, right?
Right.
Okay, in this the AND value is A0 for sure. Now, when we when we included A4 in it, then AND value changes. That means one bit from A0 got removed, right?
Yeah.
Then only AND value will change. Either one or multiple.
Yeah.
But in the worst case, only one bit might have been removed. But there won't exist a scenario where 0 bits will get removed.
Yeah, because the
AND is changing. Yeah. Now, how many bits can a number have? Let's analyze the worst case for how many such points can be present.
So 30 bits.
We have 30 bits, let's say. Let's say the number has all 30 bits set. So these are 29. These are 30 bits. If all 30 bits are set, then can we say that if we encounter one point, at least one of this bit will get reset?
Yeah.
Now, now we know that after this point, this bit got reset. Now we know what is the AND value from here to here. Right?
Yeah.
Now let's find out the next point where the AND value changes.
Okay.
So
keeping that same AND
keeping this same
A0 to A4,
A4,
and then continuing to find when it changes.
When it changes.
Okay.
Now, when the AND value changes, that means from the bits which were present, one more bit got reset, right?
Yeah.
So this way, if we observe, in the worst case, at max 30 bits could get reset.
Yeah.
After that, for sure, there won't be any set bit, so AND value will remain the same.
Exactly.
It will remain 0. So now, from this, we can observe that there will only exist 30 such points.
Right.
Now, A8, let's say, and let's say from here, like for now, we just fixed one point, right? Which is the left point of the subarray.
Yeah.
So from that left point, from here till here, let's say the AND value was A0. Then from A0, from A4 to A6, there was some other AND, and from A7 to A8, there is some other AND. Okay. Now,
and these separations are basically those points where it's changing, right?
Where it's changing.
Okay.
So we can assume that this has a AND x1, this has a AND x2, this has a AND value x3, right?
Yeah.
Now our aim is to find out number of subarrays whose AND and XOR are same is what we need to find out. Right? Yeah. Now, can we say that we know all these AND values are with respect to this point as the starting point of the subarray? Right? This point as the end point. Now our aim is to find out how many XOR, how many subarrays are there whose starting point is n, and the XOR value is equal to the AND value. That means we know that AND value for this whole range is x1.
Yeah.
This whole range is x2. This whole range is x3.
Okay. When you say x2, it's from A0 till that point, right?
It's from A0.
Okay. It's not just for that A4, A5.
No, it's not for A4, A5, A6. It's from A0 to A4, A0 to A5, A0 to A6.
Okay, got it. Yeah.
That is the AND value, which is x2.
Right.
Now, among this, if we find a point, like now it just breaks down to finding out number of R points for a fixed L, whose bitwise XOR, like let's say this is one R point and this is one R point. Right? Yeah. This is R1, R2. Now bitwise XOR of L to R1 should be equal to X2, right? Then we can say this is a subarray which satisfies the equality.
Bitwise XOR of L to R1 be equal to X2. Yeah.
Then it satisfies the given equality.
Yeah, that is true.
Similarly, bitwise XOR of L to R2 should also be equal to X2. Then only this subarray will satisfy the condition.
Right.
Given, right? So now our aim is to find out how many subpoints, how many subarrays are there whose starting point is L. However, L is fixed. So now we need to find out the subarrays with which end with R and have a bitwise XOR equal to X2 in this range. Similarly, the subarrays which end with R and have a bitwise XOR of X1 in this range. Subarrays which end with subarrays which end with R in this point and has a XOR of X3. And the sum of that will be the number of subarrays which start with L and end at any point. So now for a fixed L, we saw how we can solve it.
Yeah.
So we can fix each and every Lth point and then solve this. We just saw that for any Lth point, there can exist 30, at max 30 changing points.
Yeah.
Because they can at max be 30 bits according to the constraints.
Right.
So like we can just maintain the range of each changing point and what is the AND value of that changing point. Okay. And now to calculate number of bitwise XORs, to check number of bitwise XORs, what we can do is, we know that subarray XOR can be written as follows, right? let's formulate it. We know prefix of R. Let's say L and R are the bitwise XOR. I mean, let's say L and R are the endpoints of the subarray.
Okay.
Then bitwise XOR of that subarray is prefix of R XOR prefix of L minus 1
Yeah.
is equal to some X.
Yeah.
Now, we know for this range, what is our R? That means XOR should also be same, right? For the equality to satisfy.
Yeah.
So now for this range only, for a fixed L, we know what is L. Right? So because we know what is L, we know this also ultimately.
Yeah.
Right? So this is a known term, and X is also a known term. Right? X is nothing but X1 because we want in this range, we want how many X1, how many XORs are there, which is equal to X1.
Yeah.
So now our aim is to find out how many PRs are there in the range L to this point. Let's call it as L and this as L1. So in this range, how many prefix R's are there, which are present? So prefix R we can calculate because these two are known terms. It is X1 XOR P of L1. Okay. So now we can just maintain the prefix.
So, okay, X1 is the value we already
the
XOR we want to achieve. And P of L minus 1 we can find out based on L value.
Fixed L value.
Fixed L value. So we basically get P of R value that we want in the
range.
Right.
So now for every prefix sum, we can just maintain prefix XOR. For every prefix XOR, we can maintain the indices where that XOR appears, okay, as a map.
So if we store a map, we can get the frequency also.
We can get the frequency
of P of R exists.
So it is like we have prefix of R, and we are mapping the positions where this is occurring.
Okay.
So let's say I1, I2, I3, so on to
Okay, got it.
IX is the position.
So every prefix of R is mapped with their indices. So with that size, we can get how many such occurrences.
How many such occurrences are. So here, because we want number of prefix,
but we want it in
that
range. Right? So okay, while we are going ahead,
yeah, we can either do it while we are going ahead, or we can binary search to find how many values, because these all are sorted.
Okay, yeah. Since they will be sorted, we can just say, okay, till that L1 point only we need, right? We can.
So we'll always insert values in left to right order.
Yeah.
So it will already be sorted. Because it's already sorted, we want to know how many indices lie in the range L to L.
Yeah. Exactly.
For that, we can binary search and find out the bounds. And it depends on how you implement the binary search. Right. So once we find out the bounds, we can just
basically we find the lower bound.
Lower bound. Yeah, we can just find out. For now, let's assume we implemented binary search in a way where we found the lower bound for this.
Yeah.
And we found the upper bound for this. Yeah. Upper in the sense, the value which is greater than or equal to L is what we found. And the value which is smaller than or equal to L1 we found.
Right. So two values and the difference between the indices.
And the difference between, and the number of values will be difference between the indices.
Yeah. So
let's say right is the value whose indice value is less than or equal to L1, and left is the indice value which is greater than or equal to L.
Yeah.
Then the number of subarrays would be right minus left plus 1, right? Because these two are inclusive indices. So we add a plus 1 to include the one which we exclude. And we should ensure that in case there is no such index present, then we should ensure the value should be 0. So it depends on how you implement and how you detect that value. So this is the main observation.
Okay.
So as a gist,
the number of things we calculate is, firstly we find the prefix XOR.
we find the prefix zone.
And we also find the show the prefix or values in the map because we'll have to binary search on that.
So for every prefix or we maintain at which all index points did that prefix or appear.
Exactly.
So prefix or in which all index points did that appear.
And one more thing that we are storing is we are computing is if the partitions at which the and become and changes. Right?
And changes. Right. So here we are basically fixing the left point. And for every left point, we know there can at max be 30 changes.
30 changes.
But now the task is how do we compute this changing value? Right? So for that, one thing is once we fix L, we can't iterate, right? Why? Because already we are using a M loop to fix L. Now if we iterate, it becomes N square.
We can iterate first and then show the value.
Yeah, but though we iterate first, it depends on where we start. Because always for every starting point, these points will vary.
Right? Exactly.
So for that, what we can do is we can fix L, and then from L, let's perform a binary search. So now we know one thing, that is and function is always a decreasing function.
Right.
Basically, it's non-increase. So it might either decrease or be equal, but never increase.
Exactly.
So because that is the case, can we say that we can, like, let's say we somehow know, basically, let's say we are just checking, we know the current and. This is our current and.
Yeah.
And we want the point where the and is changing.
Yeah. So basically the highest index where the current and is still there.
Is still there. If you know that, then
and since it is a decreasing function, if the value is less than the current and we shrink the search space to the left side.
Search space to the left.
Or else we'll switch it to the right side.
Right.
And we'll keep continuing. Right?
Yeah.
Yeah.
So L and mid.
So I think, but this binary search will take n log n, right?
It takes log. It takes log n for a fixed L.
For a fixed L, but we have to go through the entire array and calculate the and, right?
We'll only go through 30 points.
Okay.
That there are only 30 changing values. So for the first time we perform binary search, in this we'll reach this point.
Yeah.
Then we'll reach the next point.
Right.
Then we'll keep reaching the end. So this jumps will only be 30. As we saw, there can only exist 30 bits. Yeah, so now from this we can see, like if we look at the search space, let L be the fixed value. Then we are calculating mid, and let left and right be our search space bounds.
Okay. Yeah.
Then from L to mid, if our current and, let and be the current and, if that is not equal, then we know that we should decrease our search space. Right?
Yeah.
Else, we should increase our search space. Now, if and is not equal to L comma mid, then that can be the new point of the next sequence, right? New first point. So we can put track of that point, new first point. Yeah. And if we want the endpoint of the previously ending sequence, it will just be index minus 1. Right? So by just doing this part, this way, if we reduce the search space, we can just get the next starting point of the new block, new range.
Right.
So here, now here, L to R, this L comma mid represents the and value from range 1 to mid. Right? So to compute this, we'll be using sparse table with O1 query. By O1 query is though we have intersection between left and right points that we need to find the value. Basically, here we need to find and. So though there is intersection between the range L to R. Let's say we found the and of L to R minus 1. And if we just AND this with L plus 1 to L, here there is a big intersection, right?
Yeah.
But still the value will be the AND value of L to R. Because though we have intersection in AND, it doesn't affect.
Repeating numbers will not affect,
Not
the,
affect
value.
the value of R.
Yeah, that is fine.
So because of that, because
The
of this
form-
property,
it will become overform.
yeah,
That is
we can use O1 query in sparse table.
Yeah.
So now if we do this, we'll be getting, after we search it, we know that we'll basically maintain the starting point. Initially our starting point is, initially our starting point will be L, right?
Yeah.
From L we are starting. So now after performing the binary search, we are finding the end point. Basically we are finding the next start point of the next range, right? So the end point will be index minus 1. Right?
Yeah.
So that means from start to end, this is the range of the current sequence, and the AND value of this sequence is AND, which we already computed. Okay? So to compute this, we could just make a query, just make a sparse query from L to the current start point. So now because we know this range, our aim is, and we know the AND. Okay? So, and we even know what is prefix of start minus 1, not start minus 1, prefix of L minus 1, because L is fixed and start is variable. So, because we know this, we can just perform the binary search, which is finding the upper and the lower point, and then calculating how many Xords exist in the range start to end.
Right.
So now we can just switch our start to the current index.
Yes.
Which is, we just found the next starting index of the next range. And this next starting index can even go n. So as soon as it reaches n, we can break it. So because like after n, there are no more points. So, and we'll reach, this index will reach n within 30 points, which we prove. So now to analyze the time complexity of this, we can say it is n into log n, right? Or we can say it as log of max of n, by because like number of ands will be the maximum number of bits in the value, right?
Yeah.
That can be the maximum. Or we can say, instead of that, we can say one more thing. Initially our and value will start with L, right? L is the fixed point.
Right.
So assuming L is the fixed point, our time complexity will be n into log base 2 of a of n, the fixed point, into the binary search that we have performed, which is log n. And for sparse, we need only one, O1 query. Now here, you might think we could even use segmentary for this.
Yeah.
But in case if we use segmentary to find the AND value from range L to mid, it would give us a TLE, because that would add up a log of n, log base 2 of n more, which the constraint isn't supporting. So the constraint is, according to constraint, we are allowed a time complexity of n into log n into log 2 of a of n, but n into log 2 of n square into log 2 of a of n is not n. So this would be the time complexity of it. And to compute bitwise Xorred, we require n time, and we are even maintaining a map. Okay? So let's assume that we are basically let's assume we are basically maintaining a map which takes log n time for insertion. Then it would be n into log n, right? Plus n into log. So this will be the time complexity. And if we look at the space complexity, it is big of n, we can say. As
For sparse table will need
Okay.
additional complexity.
Yeah.
Of course,
yeah. So n for the map of prefixes, plus for sparse table, the space would be n into log n, where n is the length of the array. So with this time and space complexity, we can solve the problem. So all these are per test case. And your n depends on test cases. So we can assume if we look at the constraints, then it's mentioned that summation of n is less than or equal to 10%. So in the worst case, there is one test case with n perfectly 10%. That can be the worst scenario.
Right.
And this TL, this time complexity is sufficient enough to pass in the given T for the given constraint.